I'll go to the first slide a second. Right. Yeah.
Okay, I think we're live now. So,
Yeah.
hello everyone, and welcome to the final demo session for the IAC MicroHack, IAC 24 edition of the Space MicroHack. I'm James from DoraHacks, and just a quick recap of what this hackathon was. This is our first mini hackathon in the space sector organized by us at DoraHacks, exclusively for students who participated in the IAC conference in Milan. And we weren't requiring anyone to build anything new. We wanted to see what students have built before in the space sector. So it was open to any student that's built any project. And I'm delighted to be here today with the winners of that, Daedalus Rocketry from the Polytechnical University of Milan. And we're going to have a demonstration of their amazing project shortly. And I'll just say a couple of words for our space community before we get started. So we're hoping with this micro hackathon, mini hackathon, that it really lays the groundwork for some future hackathons that can be organized by other space groups, whether it's a student society or an organization. If you want to organize a creative competition or hackathon, then get in touch with us at DoraHacks. We've been doing hackathons for 10 years, and our website has a platform to help you manage your hackathon and set it up, all completely free to use. So we'd love to get in touch with any student groups or any other space-related organizations that want to run hackathons. You can contact me personally, James at DoraHacks.com, or if you use Telegram, you can message DoraHacks official, all one word, and we'd love to get it set up. Or you can head over to DoraHacks.io and create your account there in a few seconds and set up the hackathon DIY style. So it's open to anyone that wants to event like this. But we're really glad, we're really surprised with the great participation in the fantastic projects that we saw apply to the IAC Space MicroHack. So we can't wait to see what further projects everyone in the community has been building. So without any further ado, I would like to hand over to Daedalus Rocketry. Welcome, guys.
Hi, thank you so much. First of all, I'd like to express my gratitude towards DoraHacks for this amazing opportunity, and also for the rewarding our project with this great achievement. I'd like to state that our project is completely self-funded, and for this reason, this money really helps us and further fund the project. I'm the coordinator of this project. I'm Federico De Martin, and today I'd like to start by stating the problem we faced in the first years of university. This is a problem that many universities face, especially here in Italy. While they provide robust theoretical foundations, they also lack hands-on opportunities. And here at the Polytechnic of Milan, we saw this gap. Students struggle to transition from theory to practice, and internships that should help them get introduced to real-world applications are hard to find. Moreover, while there are some hands-on opportunities, many of the existing initiatives are really specific and create closed compartments. In addition, access to information is often limited by disorganized resources and often also limited resources online, rendering self-learning quite daunting. As a result, many talented students miss out on the chance to apply those skills and also share them. And on top of this, then companies need to spend a lot of resources and time training new hirees for the job. So what's our solution? We didn't want just any project on the market. We wanted something that could both allow us to apply classroom knowledge and also gain new valuable skills. So why a rocket then, you may ask? Well, modern rockets were the perfect choice for us. as they are inherently complex and interdisciplinary, requiring the integration of many engineering fields like aerodynamics, propulsion, and mechanics. Additionally, a rocket provides quite a tangible goal to design, build, and launch a functioning system, something that requires both high precision and efficiency. Initially, we wanted to keep it simple, buy the parts, assemble them, and launch. But we then understood that true learning doesn't come from just combining components, but from solving problems um, ourselves. And this decision actually transformed our journey, requiring us to manage resources and not just assemble them, plan ahead, and keep a shared vision within the team. Uh, One of the most significant challenges I faced personally was balancing the different approaches within the team. In fact, many prefer to work independently and dive deeply into a particular subject, while others prefer to see the bigger picture and cooperate on a broader scale through different areas. To ensure cohesion, we hence introduce a degree of organizational structure, dividing all tasks into departments and focusing on critical aspects of the rocket. This enabled specialists to focus on their subject of choice and also encouraged many members to cooperate cross-team. I will now hand on the presentation to Elia, who is one of the main contributors in the propulsion department. Thank you.
Hi, everyone, and thanks to Federico for introducing me. I will tell you about how we developed an engine from scratch. First thing first, one of the main concerns should be testing and validating your design. Therefore, we needed many propellant grains, which could have a strong impact on our budget. Hence, we decided to make them on our own, choosing KNSB propellant for its safety, affordability, and ease of manufacture. Regarding KNSB propellant, there are also lots of valuable resources. We are obliged to reference Richard Naka's website and Martin C. Older's master thesis for their outstanding words on the topic. As you might have guessed, this decision brought up lots of legal concerns. We searched through EU and Italian regulations on explosive materials, pyrotechnics, and public safety. Naturally, our efforts were not rewarded as we had more doubts than before. At that point, we sought help from local institutions, and Milan Prefecture actually listened to our questions. After a while, they eventually sent us a document that solves our issues, stating that we could buy the ingredients and manufacture KNSB freely. At the same time we designed the engine, we used the PRO-PIP to compute stagnation pressure and temperature and the chemical composition of the reaction products. With this data and isentropic flow equations, we defined main nozzle dimensions, namely inlet, throat, and outlet radii. We developed a conical nozzle cross-section and also a parabolic one using Rouse approximation. Learning more and more about KNSB propellant led to adjusting most of these features, since we had to take into account the multi-phase flow of the combustion products. Shortly after, we got in touch with the company that built on the engine prototypes, which is one of these. And my colleagues will show you more of that later. Collaborating with OMG SRL taught us the realities of designing for manufacturing. For example, we initially selected graphite for the nozzle due to its thermal properties, but practical constraints, such as machining difficulties, led us to switch to iron conical prototypes, adding a significant cost reduction. These interactions honed our ability to communicate effectively with industry professionals and incorporate their insights into our designs. For instance, OMG support was crucial to simplify engine closure design, facilitating maintenance and preparation. In the aftermath, we explored many ideas and options that we did not use in the final design. Now, another member of the propulsion department, Paolo, will tell you more about this. Thank you very much.
Hi everyone, I'm Paolo. Thank you for the introduction, Ilya. And today I will speak about chamber materials and O-rings. So regarding the selection of materials for the combustion chamber, we initially considered three possible alternatives: titanium alloys, aluminum, and stainless steel. Knowing the cylinder dimensions, but also the maximum working pressure and the theoretical maximum temperature inside the chamber, we researched their technical properties, such as density, but also melting point, Poisson ratio, and Young's modulus. And we concluded that stainless steel was the most suitable choice. However, with the company we collaborated with, there was a possibility to use anodized aluminum, which is a corrosion-resistant material with a lower density, and we decided to opt for this material instead. So, yeah, it is this one. So, about O-rings, so securing the engine components that are cap, main motor body, and nozzle. We thought that rubber O-ring and scarf cut backup rings were the best options. The correct insertion in each groove is two backup rings at the end and one rubber O-ring in the middle. It is also possible to use snap rings for the end seal between the aluminum tube and the nozzle, but in this case it was unnecessary. However, the final decision was not to use O-ring for fastening due to communication issues with the company. Despite this, after conducting the initial test, the threading on the cap and the nozzle was found to be effective for sealing. Moving on the engine test, I will now hand them over to Federico. So thank you very much.
Thank you, Paolo. And for the record, OMG is the real company name. And yeah, well, they produced this engine. That is actually the one we used also for the engine tests. So for the test campaign, we used the NACA's test stand and with the small load. So a load cell is a force sensor that provides a small voltage difference as an output. And this one must be amplified in order to be read from our microcontroller. This is because we needed to record the thrust curve in all the tests. So for the first test, we initially used a pre-built digital amplifier, which was actually a mistake because in the first test fires, we weren't able to record the full range of thrust force. And as you can see in the presentation, I put the thrust curve, which is completely cut on the top. Despite this, given our inexperience with propellant production, as you can see also in the picture, which is pretty rudimental, to be honest, the overall testing procedure was new to us. The thrust time curves were really promising, showing us 130 newtons per second. Moreover, this was such a great learning experience, providing us areas to improve. Amplifier circuit, starting from the amplifier circuit, but also consistency with the propellant manufacturing, thermal insulation, and also since we reached 280 degrees on the outside surface of the engine, we needed greater thermal insulation. So for the second test, we did just that. We built our own analog amplifier using what we had learned in class. Realizing also the need for voltage followers, which are on the first part of the circuit. We also improved grain quality and used epoxy and cork liners for better thermal insulation. Those changes increased the total impulse to a great 211 newtons per second and an acceptable surface temperature of 170 degrees. Here I put the test video, which I think it's great. Well, of course, we were really excited for this for this test, but unfortunately, as you can see, in the thrust curve, the resolution was really bad, and so we increased the sampling frequency, and doing so, unfortunately, caused the logger crash, and so we couldn't record the second test from the second test campaign. Well, okay, here it is. For the last and third iteration, recognizing the need for more stability, we designed a custom PCB. And with this, the need for an easily adjustable gain brought us to the actual instrumentation amplifier, which is an industry standard that we now fully understand because we followed each step. Moreover, we also improved the propellant manufacturing process for greater control on heating times, also better insulation in the cooling phase of the propellant, and easier grain extraction. We are now getting ready for the final test, and as I said, the prize will be really useful to do this and getting the PCB quickly developed and built. And with everything we've learned, we now plan to fire 3 to 4 fully loaded engines for gathering precise thrust data and effectively have a trajectory to model. And well, now I'll pass the mic to Francesco, who worked on avionics.
Thank you very much and good afternoon to everyone. I'm Francesco Bosatra from the Avionics and Software team. Over the past few months, I've developed the rocket guidance and dynamic control system. We have started from scratch and we have created an operating system, Unix-like system, with a multi-threading simulation to allow the main classes to work in an asynchronous way, even if we have a 10-1, like we will say next, Jacopo, which is, doesn't allow from scratch it. The sum of all of our effort is the Cesar OS, an operating system which drives all of our part of the project. This is the operation system of the ramp, the rocket, and also the ground station. The Cesar OS relies on some classes, and we choose to separate each task in classes to minimize the possibility to total failure. In fact, all of the main principal class, which we'll talk about in a while, are independent but rely on each other to do all of the flight operation. The skeleton of our system is a sequential event control system which implement affiliate state machine. What is it, affiliate state machine? For someone who don't know, it's a model, mathematical model, and also logical, which divide all of the stage in a state, and the passes from one stage to other relies on events. So our stabilization control system can works in different mode, starting from the one we will use in most of the cases, the automatic one, which can control the rocket and all of this phase from the launch or the insertion to the landing. But also we can work it in both manual, so full manual from the ground, or semi-automatic, authorizing the stages. The other classes are Declara, the heart of our project. Declara takes the data from all of the sensor, build a state vector. A state vector is a sort of matrix in which we store and elaborate acceleration, velocity, orientation, fuel mass, etc. Declara takes the data from the state vector and build the actual trajectory and try to establish a possibility apogee point. Declara works straight together with Vale. Vale is a class which works by predicting trajectory. He predicts up to 20 trajectory possibility and compare it with Declara's one to get a more precise apogee position. With the combination of these two classes and the confront with a pre-calculated trajectory on the ground, we can estimate very precisely the apogee point and the point in which we have to open our parachute. Another one important class is the SARA, which is used to maintain a bidirectional continuous transmission between we and the rocket. The SARA has the duty to downlink all of the telemetry of the rocket, to guarantee the possibility to uplink command to the flight state machine or to the other system, and to permit in almost every case a communication between us and the agent in use. In fact, SARA is also used to communicate with the ramp. During the launch phases, we insert the order of launch to the rocket to prepare it, but all of the injection stage is on the ramp. With this trick, we can limit the risk of a self-ignite of the rocket. In case of everything we said fail, mainly a failure in the avionics and electronics, we have an abort class which do all of the things we said before, but in a parallel task. Every time he calculates a possibility impact point in case of node control, and he permits to downlink every time impact position, not the opposite, but the impact position, and guarantee, even if in case of power loss or system loss, to get the rocket almost safe on ground. Obviously, it's not possible to guarantee that 100% of safe in case of abort, but we can limit the possibility damage. So I can take the stage to Jacopo, which developed our electronic part and hardware, and our last plan in case of power loss, the automatic recovery.
Okay, thank you.
Thank you very much.
Thank you. Good afternoon, everybody. My name is Jacopo Dare, and as Francisco has introduced me, I will talk about the hardware electronics. Well, as Francisco has already discussed, parallelization is a key aspect in order to save ourselves from any possible failure case. When SARA could have a fail in transmitting data from the rocket to the ground station, or if the extended Kalman filter doesn't fully operate within the classes of Vale and Clara. This is why the evaluation must follow two principles. The first one is to have a very specific and accurate sensors in the avionics unit, and then have a backup plan in case of a complete failure of our microcontroller. Starting from the hardware we chose a Tensy 4.1 as a microcontroller, which has a timekeeper incorporated, but which does not fit completely our needs, and this is why Francesco developed a more precise timer protocol. Later, the avionic and the sensors are composed by an inertial measurement unit and a barometer, which you can see on screen, and this is how we will transmit the data collected during the flight to the Tensy, and the Tensy will perform the evaluation in order to calculate and evaluate the expected apogee point where we plan to deploy the parachute. In case of a failure of the system or a temporary lack of tension, we have a backup plan. This backup plan consists in adding an electronic parallelization to the timekeeper that is performed by the Tensy. And this works by applying NI and NE555 in monostable configuration. And this implies that the NE555 is characterized by a resistor and a capacitor. And whenever the Tensy performs an evaluation for the expected apogee, we transfer this very specific value to an EEPROM memory, which is part of a digital potentiometer. The digital potentiometer allows us to switch dynamically to one of 256 steps, and therefore characterize the resistance of the resistor, and therefore it allows us to change the time that NE555 must wait before sending a high tension value to the MOSFETs that will ignite the deployment of the parachute. This digital potentiometer is the key for this system to work, and the Tensy and the NE555 are connected by a series of logical gates, AND gates, and XOR gates in order to maintain a preference whether the Tensy is still fully operational. And this is it as far as backup timer and hardware. No, actually, there's still the radio unit to be implemented. Yeah, but now I'll leave the floor to Ludovico. Okay, no, there's still Francesco for a quick add in the end.
Yes, sorry. I have to add one little things that our Cesar OS can, in case of a power loss and a power restore in the air, to calculate the present position and rebuild all of the state vector, even if the rocket is in flight, because we record all of the event. So in base of the event, it can understand in which phase of the flight is it, and it can restore and save the mission, even if a power loss is a catastrophe. I leave the stage to Ludovico. Sorry for that.
Okay, thank you.
Okay, thank you. Hi everyone. Good afternoon. Yes, so I'm part of the structures department. Specifically, I've been working on 3D printing and design of the nose cone. So starting with 3D printing, the main challenges I faced, I've been learning about tolerances, dealing with printing times and volume, and general issues related to the printer itself. Everything came down to trials and errors. For example, I immediately faced with the so-called warping, which is a problem that occurs in 3D printing when the melted plastic cools down too quickly, causing it to shrink and detach from the adhesion plate. This, in most of the cases, brings to an inaccurate print, and in the worst cases, to a total print failure. As you can see in this image, I took one morning after a long night of printing. It was not good. So this happens when the object completely detaches from the plate, and the printer just keeps extruding the plastic onto nothing. This problem has been solved throughout the accurate leveling of the adhesion plate, the setting of the nozzle and ambient temperatures, and many other features, with many failed prints before reaching a satisfying success rate. So, like, if you can watch me here, I have a lot of like failed prints. Maybe you can't see everyone's, but I can assure you it's full of failures before getting to a success, like a good success rate. So going on, now about the nose cone. The nose cone is the biggest 3D printed part of the rocket. Since 3D printing takes a lot of time and has limited printing volume, I had to divide the nose cone in different parts to optimize these aspects. What you were seeing in the video is, in fact, the nose cone. I have one here. This is not only one piece, but you can see we had to divide it to optimize the volume and the time that it takes to be printed. Additionally, the nose cone is strongly integrated with the recovery module. Unfortunately, today our recovery team member Stefano couldn't be here, so I will try to say as much as possible. But so I work closely with the recovery team to find a successful design. The first prototype, as you can see in the image, it had a single chamber with both the charges and the parachute. The parachute was inside our deployment bag, but still the risk to damage the parachute was too high. So we switched to a ring-shaped chamber, only dedicated to the charges, as you can see in the image. This reduced actually the risk to damage the parachute, but it was not ideal for the ejection because of the much smaller area on which the pressure would have pushed. Now we are working on a new solution. This is still work in progress, but this is the idea. So a single chamber with diffusers to protect the parachute. So in order to get to this consideration, we run many expulsion tests, but I will let Andrea speak about them later. Thank you.
Hi everyone, I'm Andrea from the structure team of Daedalus. Working for Version 1 has been a challenging yet rewarding experience, teaching us the value of collaboration. One of the most remarkable aspects of Daedalus is how each member contributes beyond their specific role. In fact, as Ludovico said, I worked on the parachute aeration module test, preparing the explosive charges and working to improve gas insulation to prevent the pressure inside the nose cone from dissipating. Together with Luca, I also built this insulating cylinder to isolate the propulsor from the engine block. This is the entire engine block. I also joined the propulsion team for tests, developing the O-pump circuit with Federico and helping with the production of propellant. This cross-team collaboration is what truly defines Daedalus rocketry. It is about pooling our skills and knowledge to achieve altogether a shared goal. Now talking about the engine block design process, our initial design was often smaller or thinner than expected. sometimes also deformed or melted, as you can see in the picture. To overcome these challenges, while developing the engine block, we adopted an iterative process, designing, printing, and testing our components. Each iteration obviously brought new insights, helping us to improve our designs. We had problem also with the design of the small fins of the engine block. Initially, it was designed with a thin 1 millimeter PLA sheet, but this design was too fragile and prone to breaking, as you can see in the picture and in my hands. So I redesigned it with a thicker, more robust parallel pipe, which also significantly improved the structural integrity of the whole engine block. Even the aerodynamic design of the fins proved more challenging than expected. Initially, I found some recommended dimensions online, and I integrated them to the engine block, thinking it would be straightforward. But when Filippo, our aerodynamicist, ran simulations, we realized that the initial design didn't meet the aerodynamic requirements, prompting further refinements. Now I hand it over to Filippo. Thank you all for your attention.
Thank you, Andrea. Good morning, everybody. As he was saying, the characterization of the fin was one of the main challenges of the aerodynamic part. And as you can see from the table here, this two-sweep angle geometry was in fact something very difficult to simulate and to understand. And it brought a lot of induced drag and vortices. So we opted for a simple geometry and also to be able to use a lot of technical reports so as to validate our solution and our geometry. For this simulation, we used the ANSYS software. We use it extensively from the geometry part to the simulation part. So we had to understand from zero not only the software and the aerodynamic part, the software, okay, and all the characterization and the parameters used in this case to better understand the phenomena occurring in the rocket. We used the contour and path lines instruments on the ANSYS simulations. That was really useful. With the software and as the aerodynamic part, we characterize the boat tail and the air brake. The boat tail is a part at the end of the rocket which helps to reduce the volume in which the vortices are generated and to reduce the turbulence and the induced drag. And as we can see, the 20 degrees version was the latest one and the most aerodynamically. But for propulsion and structural constraints, we had to go back to a previous version of the 45 degree. From this analysis, we found out and learned about the trade-offs. Trade-offs is something, in fact, very diffuse in engineering, and we learned to do the best choose considering all the aspects between a project. For example, is you had to consider aerodynamics, structure, and propulsion. Now, speaking about air brakes, I will hand the microphone to one of my colleagues, Michele. Thank you for the attention.
Hi all, I'm Michele, and today I'd like to take you through to our rocket air brake project, introduced by my colleague Filippo. This project has been both a major challenge and an invaluable learning experience. Imagine trying to stop at a red light, but in the air, with no brakes, no road, and definitely no other cars. Sounds easy? Well, it's not. Aerodynamic stability is crucial for keeping the rocket on the right trajectory during ascent. And we ask ourselves, why not apply the same principle during descent? Our idea was to use air brakes placed just below the tip of the rocket to slow the rocket down during ascent. And once the descent began, the air brakes, thanks to the excessive drag generated, would reverse the center of pressure relative to the center of mass, creating a kind of reverse stability. We immediately set to work designing elements that were as simple and reliable as possible, starting with a model featuring flat surfaces extended radially. Over time, we arrived at a final prototype that we thought was truly innovative, with actual walls extending from the rocket body. We also explored many different ideas for the internal mechanism. Each idea met certain needs, but also brought its own set of challenges. Essentially, it was a process of constant trade-offs. The geometry of the air brake is designed as a circular sector, which is whipped extrude along the circumference of the rocket. When fully deployed, the air brake exposes a portion of the rocket's cylindrical surface to the airflow. This interaction with the air generates the corrective drag needed for stability. To finalize the dimension of the air brake system, we used a parameterization approach. The goal was to find a balance that minimized the component's volume and weight, while maximizing the exposed surface area to enhance the correct drag available. In theory, this solution should have improved stability, but during simulation, we realized that the airbrakes worked, perhaps a bit too well. They slowed the rocket down to the point of creating excessive turbulence, which risks causing dangerous rotational motion along the perpendicular axis. At that point, we decided to pause the project, realizing the challenges involved in designing such a complex component from scratch. This work required a mechanical aspect for the physical design of the air brakes and an analytical aspect for simulation and study of aerodynamic behavior. Collaboration between teams was key as it allowed us to quickly identify the problems. However, the project was not being abandoned. We have learned a great deal about aerodynamic analysis and computer simulation. We're happy to share what we learned through tutorials and resources, so others can learn from our experience. But my colleague Julia will now tell you more about that.
Thank you, Michele. Good afternoon. I'm Giulia, and my contribution to this project focused on developing educational materials about ANSYS simulations. And before getting into details, let me explain basically what ANSYS is. ANSYS is the software they showed before, and it's an engineering software. And it's really used in fields like fluid dynamics, structural mechanics, and thermodynamics. We used it a lot in our project to study aerodynamics of the components of our rockets by testing them virtually to improve the key parts. But the problem is that ANSYS may not be the most intuitive software, and it could be pretty complex to use it. Moreover, in universities programs, it's not taught so early. So, as we said before, university are really good at teaching theory, but they don't always give the chance to get hands-on and learn from scratch. So, in order to bridge this gap, I recently started creating educational materials and modules in both written and video format. I tried to combine both theoretical and practical information. So that's how I organized the presentation, as you can see in this slide. And you can see also an example, which is the little fin that was previously designed by Andrea, and my role was to test it. And in order to prepare it for these tests, we had to follow 3 steps. The first one was to adjust geometry. The second one was to set up boundary conditions. Boundary conditions are basically how the simulation interacts with the surroundings of the body. And the third step was to test the different angles of attack. The angle of attack is the angle between the fin and the upcoming flow. These three steps may involve new concept and require an interpretation of aerodynamic data. So our idea was to turn these steps into something easier to learn, and in order to make it accessible to a wider range of people, and to help learners to use not only what they already know, but also the hard skills they learn from scratch. So now Sasha will talk about our vision for the future.
Thank you. So, as we've seen up to now, making a rocket has been a very important part of our journey so far, but it's never been the ultimate goal. What we've always been about is developing a robust educational model and framework around rocketry. As soon as we do our first launch, we plan to let new members come in and mentor them and allow them to essentially build the same rocket that we've built, but from scratch, and allowing them to experiment with new designs, new methods, but always having our mentorship at their side. And this is important because it will allow our documentation, of which we've just talked about, to develop and become an ecosystem which can be available for future use and newcomers. The point of all of this is to build something that is truly open source, but it's not really enough to be open source. In engineering, too often our accomplishments overshadowed by the unending hours spent on failed designs and failed prototypes. So what we really look forward to doing is helping people understand that these are the crucial moments in an engineering environment. And our documentation, which focuses on the personal experiences of people, the steps they took to overcome specific issues, and testifies to a real-life encounter with challenges and hardships, should help them. Because having a mentor is one of the most important things that one can have when they're trying to solve an engineering problem. And we've experienced that at firsthand. So we hope to be able to be that mentor to other people through our open source ecosystem of knowledge. And we're truly committed to this idea because sharing isn't just beneficial to others. Sharing is beneficial to yourself too. When you describe your work comprehensively, you gain a deeper understanding of it. We look forward to working with universities and companies to develop an ecosystem of knowledge where research and understanding is cultivated and ultimately applied. So it's truly our ultimate goal is that of creating this repository of information. So thank you again for listening and staying with us up to now. I'll pass the mic to Federico.
Thank you so much for this inspiring vision. This was a really difficult project to put together. And in the end, we are really grateful for this achievement and this recognition from DoraHacks. And well, now if you have any questions, we are here to answer them. And I'd like to invite all of the team behind us. If you could adjust the camera. Yeah. And here we are. There's not everybody today. Some were busy with university. But really, thank you so much. Yeah. Yeah, come. Yeah.
There we go, guys. thank you so much for that presentation. You've had a whole crew involved. It was great to hear from each of you about the challenges you faced and your expertise that you've managed to share with everyone during this. So thanks to everyone and congratulations.
Yeah, thank you so much. Unfortunately, I'm the only one hearing, but congratulated with everybody. And
Thank you.
I myself want to express my gratitude to your work. Here we are. Well, yeah.
Yeah, that's fantastic. So if anyone in the audience has any questions that they would like to ask, feel free to type it in the comments section. I'll give you a couple of minutes. And just then, as we wrap up this final demo session for the IAC 2024 MicroHack, it's been a great journey. We were really amazed by the participation that we had from all of the projects, from all of the teams. So you can head over to check out all of the projects that were submitted to the MicroHack at the hackathon page on DoraHacks. So please do check that out. I really hope that this is the start of something in the space sector, that we see more hackathons like this and more activities. And we're all about helping early stage projects with getting the funding they need to develop into the future. So just from me here, while we're seeing if anyone from the audience has any questions, what would you say is next for Daedalus? I know you've touched on the vision and creating that repository of knowledge and information, but is that the next step, or is there anything else you'd like to share with everyone?
Yeah, we'd like to prove ourselves with an actual functioning launch, and after that actually develop the whole system. We are currently developing also all the modules, so the only step we need to take after the launch would be to organize it into these repositories. I take this moment to also thank you personally, as you helped us with also all your tech stacks, and we are now getting into the intricacies of licensing our technologies and our documents for open source purposes, of course. And yeah, getting ready for the launch is, of course, quite a big task. And for this reason, as I said before, we are going to have a third test, the engine test phase, with a lot more engine and fires. So we'll keep you posted on our social for sure for that. And yeah, after that also, we'd like to add and develop a better understanding for the aerodynamics and introduce also the air brakes, as Michele told us before. And yeah, but in general, our vision is to truly bring something from scratch to actually a complex system that may also have in the future maybe thrust vector engines and more control on the whole system. Yeah, the next steps are those.
Amazing. Yeah, I'm glad we've been able to support you up to this point and look forward to working hand in hand going into the future. I can see a question we've got from Dominic here. So Dominic asks, if you were to advise others on starting a project like this, what's the most important What's the most important pitfall they'll encounter? So you talked about some of the challenges. What would you say is one of the most important ones that they might have to watch out for?
Personally, as I said, ensuring that the vision for the project is united among the team. And that's for sure a constant challenge up to nowadays. When someone new wants to enter the team, we must be sure that they have a comprehensive understanding of our objectives. This is for sure one of the first problems that comes to my mind, but also the impulse to rush and to maybe try something as the digital amplifier or the air brakes, despite this being sign of ambition, they are truly hard to bring to life. And yeah, this is something that made us slow down in the first phases, and now we are way more organized, and also we have, as I said, a shared vision, so it's way easier to pull through these issues.
Great. Yeah, awesome. Thanks. You can tell just from the presentation today that you've all been so aligned on the vision. It's what's made the project such a success. So great to hear. So I will just finish by adding that, once you've once you've submitted your project as a buildle, it's just a nickname for a project we have on DoraHacks. It is there. You've got it listed on the DoraHacks database, and you can use that to apply for further funding. I've put a link to the space mini grant that we have, which is available for all space communities or projects. If you need funding, just explain to us what you'd use the funding for, so you can go ahead and apply. That's that there. So you can use your existing builder if you're another project that is applied to this hackathon, or you can create a new one if it's a new project. We're really looking to support these early stage projects and growing communities of space enthusiasts and professionals. So do check that one out. And I think that's all from me. If there's anything else anyone from your squad wants to add before we finish.
Would you like to add something?
That's fine.
Well,
okay, no worries. I think it would take too long to go one by one. Yeah, well done. It was a long session, but thank you for all of that.
Yes, we're very grateful to you for your continued help, and again to everybody who listened to us so far. So only that.
Okay, great. Yeah, thank you. And to everyone in the audience, make sure you're following Daedalus Rocketry on their social media to keep up with their updates. Same for DoraHacks as well, so you don't miss any future space hackathons that we have. And yeah, I look forward to working together in the future. Thanks, everyone. We'll call it a day. Thank you.
Bye-bye.
Bye.
Thank you.
Thank you so much.
Bye.
Bye. Bye-bye.